So far this year, we've really talked about gravity as the downward force that pulls objects towards the earth. So I've drawn this person with a downward force, and then we've talked about there being other forces that stop them from moving, like the normal force. But why is it only the earth that pulls objects towards it? Like, why isn't this person pulled towards this other person? Or why aren't they pulled towards the ceiling? Or towards the globe on this table? What makes the earth special? Well, if you go through the list of things I just said, the earth is huge. These other things are not that huge. So maybe being big has something to do with it. We also know that in our solar system, there's not just one huge thing. We've got the sun for sure, but we've got several planets: Mercury, Venus, Earth, Mars. The sun pulls on each of these and holds them in orbit. But the Earth is not just pulled on by the sun, it's also pulled on by its own moon, and it's pulled on by Mars, and by Venus. So there's not just one force of gravity, there's actually many.
It turns out that gravity is actually a force between every two objects that have mass in the universe. It's a universal force that affects everything. And that's what this unit's going to be about, to try to understand how that universal force works and to try to make some sense of its patterns. The nice thing about a universal force is you can never get the question wrong about what's pulling on you. Everything is pulling on you. So here's a list of things, ranging from the obvious to some of the weird, of stuff that is actually pulling on you. Literally everything in the universe. If you look at patterns, the ones that seem to matter are ones that are both big, which I've checked off in red, and close, which I've checked off in green. So the close part, we understand that. That's the inverse square law.
When we talk about massive objects being important for determining whether the force of gravity is big or not, we have to remember that it's not just the mass of one object that's important. If we take this person falling towards the earth, clearly they have a force of gravity on them. But you have to remember Newton's third law. If earth pulls person, person pulls earth. They're both involved. And those two forces are equal and opposite. So if we're going to say that mass is one of the things that affects the size of the force of gravity, we really have to consider the mass of the planet and the mass of the person. They both matter.
So up till now, we come up with this idea that the force of gravity is proportional to 1 over the distance between two objects squared. We've suggested it's also proportional to the size of the two objects. So here's where we stand with an equation. As we've seen before, just because things are proportional doesn't mean they're equal to each other. What if the equation was simply the force of gravity is m1 m2 over r squared? Think about the person you're sitting next to. Let's say you're both 60 kilogram people, which is a fairly normal size. Let's say you're a meter apart from them. That would imply that you have a force of 3,600 newtons between you, which is basically 800 pounds. So clearly that's not the case. There must be a constant we multiply this number by to get the real force of gravity. So here's our constant k stuck into the equation to turn the proportional sign into an equal sign. And since this constant is so important as it's going to determine the force between every two objects in the universe, we give it its own letter. We give it the letter capital G. So what is big G? We can't really use the equation to get any values for forces if we don't know what it is. Could we get it experimentally? If you were trying to solve this equation for big G, you would need to know the weight of an object, the mass of an object, the mass of the second object, and the distance between them. So we can find the weight of something on Earth, but if Earth is one of your two objects, what's the mass of the Earth? Anything close by to us has such a small mass that trying to measure the force between any two normal objects is nearly impossible because it's such a tiny force. It took more than 100 years until a guy named Cavendish in 1798 built this apparatus. At the heart of the Cavendish apparatus is this thing, what's known as a torsion balance. It should be noted that this thing you're seeing with Christmas ornaments is just a model to demonstrate how a balance works. A real one used very massive objects made of lead and was very much protected against outside forces. This is just so we can see how it behaves. Notice I have two weights suspended from a stick, which is hung by a string. At the heart of the Cavendish, and the way it works is that the very tiny force of gravity between the large weights and the small weights, if we move the large weights around, it can change the direction of that force. And at first they're set up so that these weights are tugging on each other. The small weights are on a big stick that can rotate, and big weights are put in line with that stick. So the force of gravity on the two small weights opposes each other. Everybody stays put. We then change the configuration of the spheres. We now expect there to be a force to the left on the bottom and a force to the right on the top. That's going to cause the rod to twist. And we'll be able to measure how much it twists by observing the string. If you arrange it like this force of gravity is up, this force of gravity is down, and that causes the stick to twist. How much it twists tells you how big the force is. If you ever played with a tire swing as a kid, you understand the basic physics of this. Let's take a look at one. So here's a tire swing, and it's very much like a mass on a spring. If I give it a rotation, you'll see it starts to go back and forth. And basically the torque on it is increasing the farther it turns. The more angle it turns clockwise, the more torque counterclockwise it gets, and vice versa. So hopefully you understand if you twist the string more, it applies more force to twist back. This is actually a special kind of rotational force known as a torque, but that's not super important for understanding what's going on. The more gravitational force there is to the side, the more the string is going to twist, and the more we'll be able to measure it. So obviously this experiment has to be done in conditions where there's no motion, either due to my hand moving, due to the wind, and actually what's been a problem for me all morning trying to film this, it needs to be a cat-free environment. You're going to watch the Cavendish experiment as done by Professor Gerald Zacharias of MIT in an old PSSC video from around 1960. You're going to see Professor Zacharias take huge precautions to shelter this stick with weights on it, because you can imagine the forces between any small weight due to gravity are going to be really small. You don't ever notice two weights sitting in the classroom pull on each other. So he puts it in a glass box. It's a very long string. It's hanging it. You can see in the 1798 Cavendish apparatus that Cavendish actually looked in through peepholes on the side to try to minimize wind and other forces. So at this point, please pause this video and watch Professor Zacharias do the experiment and then come back. All right, welcome back. Let's see what we can do with the kind of data he was collecting. It's going to help us get a value for big G so that we can then use this equation to figure out the force of gravity between any two masses. One of the neatest uses we could have for this equation is to solve for what the mass of the Earth is, or maybe what the mass of other planets are. The data from the Cavendish experiment can be used to find a value for big G of 6.67 times 10 to the minus 11th. I have that written out here, not using scientific notation. And it's pretty obvious that it's a tiny, tiny number. And that's our explanation of why we don't notice people pulling on each other gravitationally. If this is our universal gravitation equation, if M1 and M2 are, say, 60 and kilograms and 70 kilograms, you multiply that by this tiny little number, it's going to make the force essentially zero. That's why we don't notice it. But this number is involved in figuring out how hard everything pulls on everything else. Without it, we can't use the equation and solve for things like the mass of a planet. But once you have big G, a very simple experiment allows you to weigh the Earth. I've got here a 500 gram mass, half a kilogram. We're just going to hang it from our spring scale. And we can see we get a value of about 4.9 for the weight of this half a kilogram mass. That will allow us to get the mass of the Earth. You saw the scale gave a reading of 4.9 newtons, and we know that the hanging mass was half a kilogram. We don't know what the mass of the Earth was. We'll call that M2. So with big G and knowing the radius of the Earth, we should be able to get how much the Earth mass is. So here's the math to figure out how much the Earth mass is. You can see I solved it without numbers first to try to make my life a little easier, so I'll walk you through it. Here I multiplied both sides by the distance squared, which gave me distance squared FG equals GM1 M2. To get M2 by itself, I then divided both sides by GM1. So M2 was d squared FG over GM1. So I plugged in the radius of the Earth, I plugged in the weight according to the scale, I plugged in the mass we were talking about, plugged in big G, and solving it all down, I end up with that as the mass of the Earth. Quite big. Alright, so we're left with this equation for Newton's law of gravity. I just want to clarify a little bit on notation because you may see this written different ways. Notice it says R on the bottom. It's important to recognize that that R stands for distance, the distance between two objects. It sometimes connotes the idea of radius, and that's because we have to remember gravity spreads out spherically from an object. So yeah, the distance between me and Oscar the Grouch is the radius of a circle surrounding me as my gravitation spreads out. But don't think it's anything other than just the distance between the centers of mass of the two objects. That's why sometimes you'll see the equation written like this with a D down there. You got to be careful because sometimes you might want to think that that means radius and diameter. It's not. It's just the distance between the two centers of mass. So don't get messed up with that. Another reason for using R sometimes is if you're talking about somebody standing on a planet, the distance between the center of the planet and them essentially is the radius of the planet. So that's why there's some confusion. Just be careful with it. So I hope at the end of this video you understand that the force of gravity is a universal force between every two objects that have mass. The strength of this pull depends on the masses of the two objects. Previously we learned that it also depends on the inverse square of the distance between them, which accounts for the spreading out of gravity from an object. In this video, I hope you learned that there's also a constant, which is a very tiny number, and now you know a little bit about the history of how we got that constant. In addition, you should know that the force of gravity we usually think of is really the force of gravity of the Earth pulling on us. But if you're thinking about all the things that are pulling on you, there's many things. There's actually an infinite number of things, everything in the universe. So to figure out the gravitational effect of all that, you simply add up all those forces using a free body diagram and sigma F equals ma and such. What's left to do is practice using this equation and also to try to figure out what its relationship is to our earliest equation for gravity, which is just Fg equals mg. So that's what we'll do next.